Today we're going to be talking about finding derivatives using the definition of a derivative. So this is where you're to first learn in a calculus class to understand what a derivative actually is and the definition behind it before we can actually derive some rules which makes finding derivatives much easier. First, what we've seen from previous videos is that we can find a slope of a curve or an average slope between two different points. So let's say we wanted to find the average slope between point 0 or x is equal to 0 and x is equal to 2 in this specific case. You just use delta y over delta x. And our second y point is at 4, or x squared, because that's our function that we have in this graph on the left, minus 0 squared, which is 0, divided by delta x, which is 2 minus 0. And so in this case, our average slope between our 0, or x is equal to 0, and our x is equal to 2 point is just a slope of 2. So if you drew a line between these 2 points, it would have a slope of 2. This is talking about the average slope, but if we want to find a formula in order to find the slope of every single point, what you end up doing is using the definition for a derivative for the specific case. So a derivative, or dy over dx, which is just the derivative of our function y with respect to x, is also equal to, this is the limit where h is approaching 0, and on top, instead of y2 minus y1, we're going to have something called evaluating our function at f of x plus h, or f of x plus h, minus f of x, divided by h. This is the definition of a derivative that you'll see within your textbooks. And this is essentially the same thing as saying y2 minus y1, just in a different form. And I'll show you right here. If we do y2 minus y1 over x2 minus x1, we're going to have the same thing with our limit of h going to 0, where we're making that x plus h very, very small, which is essentially just f of x. So f of x plus h is our essentially y2, or our second y point, minus our first y point, divided by x2 minus x1, where our second x point is x plus h minus x. And so we actually just cancel out the x's, and this is where you just get h on the bottom. So as h approaches 0, we're basically finding the derivative at a single point. So let's learn how to actually use the definition of a derivative here. If we have our function y is equal to x squared here, f of x is the same thing as saying y. Where we usually use y in our classes, but f of x is also the same thing as saying the function that we're using with respect of x. So in this specific case, if we want to find our dy dx, we're going to find our function with our limit of h going to 0. It's very important that you write this down every time. Most professors will take off points if you don't carry the limit over. And now, wherever our x is within our function of y, we're going to plug in x plus h for that. So instead of x squared, we're going to have x plus h quantity squared minus x squared divided by h. Now, if we can prove this evaluates to a specific function where h is going to 0, then we can actually find our definition of our derivative, or we can find our derivative of x squared at every single x point, which is really cool. So if we take dy over dx, carry that down, is equal to the limit of h approaching 0. If we expand our quantity here, we're going to have x squared plus 2 times h of x plus h squared minus x squared, still divided by h. We can see our x squareds will cancel here because we have an x squared minus an x squared. And so we can rewrite it as the limit of h approaching 0 of 2h of x plus h squared divided by h. And now we can simplify some of these h's since we have h's in every single quantity on the top and on the bottom. We'll do the limit of h approaching 0, where h's are canceled out, where we have 2x plus h. Now, with this specific form, it's really nice because anytime you have h approaching 0 and you don't have any h's in your denominator, which is a key factor here, we can just evaluate h is equal to 0 for the specific limit. So when we just say h is equal to 0, the definition of our derivative gives us the function for 2x for every single x point for x squared. Whenever x is equal to 0, the slope at that specific point has a slope of 2 times 0, which is just 0. So it would be a horizontal line going through this specific point, which is true. If we do the same thing for x is equal to 1, we're going to have 2 times 1, and our slope should be 2 for the line that you would draw corresponding to this tangent line here, which is what it would end up being if you end up finding the slope of that line. You can end up finding the derivative functions of any single function that you're given, and so let's go through some practice. So for this first one here, we're going to have a polynomial where we have a cubic term and some other terms, and we're going to try to find f of prime of x, which is the same thing as saying dy dx. So we're going to use the same formula here, where we have the limit of h is approaching 0. Now we have to remember every time we have x in our specific function, we have to replace it with x plus h. So we're going to have x plus h cubed plus x plus h plus 1 minus x cubed minus x minus 1. Because I already distributed the minus sign that would be in within the formula that we've seen before, divided by h. And so we can cancel out some like terms already, and we'll do that on the next line here. So the limit of h approaching 0. We still have this quantity that we'll have to expand here in a moment. But our x's and 1's will cancel out, so we'll have x plus h cubed plus h minus x cubed on top divided by h. Now when we expand that quantity, x cubed is the same thing as saying x plus h. So that quantity squared, and we just solved for that on the last page. X squared plus 2x of h plus h squared plus h minus x cubed all over h. And now we have to do, distribute both the x's and the h's in order to solve for that quantity again. When we expand the quantity up above, we can also use the binomial theorem if we end up understanding that, or we could just distribute, and you should end up getting x cubed plus 3xh squared plus 3x squared h plus h cubed plus h minus x cubed from the before divided by h. And so you get the limit of h approaching 0. We can cancel out our x cubes, and we also have an h to divide by. So if we cancel out our x cubes and we divide by h already, we have this that's left over. And so when you can plug in h in this specific case, because there's no h's in the denominator anymore for this specific lesson, we'll end up getting 0 for this term here, 0 for any h terms, and we'll be left with 3x squared plus 1. So this would be our f prime of x for the specific case. Let's do it for the specific function here. So this is 1 over x, or x to the negative 1 power. And let's find the derivative of this specific function. So f prime of x is just another way of writing it. We're going to use the limit of h approaching 0, where we have 1 all over x plus h for the first term, minus 1 over x divided by h. To actually solve for this, we need to combine the two fractions above. So let's do a little aside on the bottom here, where we have 1 over x plus h, and we're subtracting a fraction with a different denominator. So what you can end up doing is multiplying or cross-multiplying like this, and those will be added together in the numerator. So x times 1 will be x minus x plus h times 1, which is just x plus h, divided by the denominator multiplied by each other. So you get x times x plus. We can combine these two fractions and solve it into the above equation, where we have the limit of h approaching 0. And we have our numerator as x minus x plus h, which is the same thing as canceling out our x's. We have h in the numerator. And in our denominator, we're going to have h, which is still down here, multiplied by x times x plus h. So we're really going to have h times x plus h. And the last thing that, if you're not careful, like I ended up doing in this problem right here, is that we have to carry over this minus sign to this h. So we're actually going to have a negative h divided by h times x plus h. And so now we can cancel out our h's because we have them in both the numerator and the denominator. So we're going to have negative 1 all over x times x plus h. And our limit of h approaching 0. And in this specific case, since it's x plus h in the denominator, and we're not going to have 1 over 0 we'll end up getting negative 1 all over x squared, which is the derivative of 1 over x in this function. So we can use this function in order to find the derivative or the slope at any single point along this function. Let's look at an interesting function called e to the x. And the actual interesting thing is that the f prime of e to the x, or the derivative of this, is just the same function. So let's see if we can actually find that using the definition of the derivative. So the f prime, using the definition, with a limit of h approaching 0, and we have f of x plus h, so we need to do e to the x plus h minus e to the x divided by h. Two things with the same bases multiplied to each other ends up adding their exponents, so we can actually reverse that operation. So we can actually deconstruct the e to the x plus h, e to the x times e to the h, minus e to the x divided by h. We can actually factor out the e to the x's in the top portion, where we're going to have e to the x multiplied by e to the h minus 1 divided by h. And so if we can prove that quantity is just 1, we end up getting the right answer here. But in order to actually solve for this, we actually need to do something called an expansion of e to the x, or e to the h in this case, where this will most likely be given to you if you're in a beginner level math class. But e to the h is also the sum of this specific set of functions. It's the sum of the specific basis functions here, h to the n divided by n factorial. So it's really the same thing as saying 1 plus h squared all over 2 plus any term that has higher powers of h higher than 3. So we can use that, plug it into our e to the h, and end up hopefully solving for our limit here. So we do the limit of h approaching 0, multiply by e to the x, and we plug that into our numerator here. We're going to have 1 plus h squared divided by 2 plus oh of 3, which is just anything higher in terms that we're not really going to care about in this specific case, minus 1 from before, divided by h. So now that we can see, we can have terms that we can cancel out in the numerator. So if we rewrite this, we have the limit of h approaching 0, e to the x, multiplied by now our quantity after also canceling out the h's. We have 1 plus h over 2, plus now oh to the second power, because oh to the third power divided by h is just the same thing as saying terms of h squared and higher. And now, since we have no 1 over h terms where we get 1 over 0, which is when we can't plug in 0 for our h's, and now our h over 2 will go to 0, and our oh squared will also go to 0, leaving us just with e to the x multiplied by 1 is just going to be equal to e to the x. And so now we prove the f prime of x is just going to be equal to e to the x for the function e to the x, which is really cool. I hope you have learned something today about using the definition of derivatives. Please like this video and subscribe to my channel for more math and chemistry related videos.